Good afternoon. I am Jaitirth Managoli. I represent AMSC in India. I am looking after the sales and marketing. I am not a simulation guy or a studies guy. After doing all these simulations, what do you do? So probably I am going to talk about the solutions for the the problems which are encountered in the integration of the renewable energy. A little bit on the AMSC. AMSC is American Superconductor. We are in the business of superconductors and also power electronics. That's STATCOMs. We also license wind power, wind turbine manufacturing technology. We are based out of US, and we have experience of about more than 100 wind and solar farms solution in meeting the grid codes. So the topic is application of STATCOM systems at the wind farms, basically for improving the dynamic performance of and to meet the grid codes. So we have been talking about the issues for integration of renewable energy, large scale basically. So the main problem for these renewable energy is the variability of the resource, and that is inherently unpredictable. The variability of the, it's variable. So there are a lot of challenges. That's number one. Number two are these things are basically because of the land requirements. They are located at remote places. So that also poses some challenges to the operator. And because of this, there can be heavy transmission congestion issues. So this all drives the operator to issue some grid codes which they would like to see all these renewable energy power plants as a conventional power plants. At the point of common coupling, they want to see the entire renewable plant as a conventional plant. That's why they come out with the grid codes. So basically these grid codes talk about the voltage ride through or dynamic capability, then the power factor capability, the control objective, and power quality, flicker and other things, and how do you validate all these compliances. So if you talk about the worldwide grid code requirements, there are many countries who have already have good, well-established grid codes, say the Canada, the Brazil, the South Africa, Australia, UK, Romania. India is on the way to establish a grid code, especially for renewables I'm talking about. So basically all these grid codes are on the basis is the same, but depending on the location, depending on the country, there are some pluses and minuses. So some important requirements of this grid code is this grid code requirements talk about meeting the requirements at the point of common coupling. That could be on the high side of the transformer. That could be a transmission voltage level. Then when you talk about the reactive capability of the wind farm or a solar farm, they have some reactive capability. So that's the one. Then there are some capacitor banks are also installed in the power plants. So how do you integrate all this together to meet the grid code? There could be some requirement of STATCOM in some of the wind power plants or solar power plants. So you also need a control capability, control systems which are creative to pull in all these resources to meet the stringent grid code at the point of common coupling. So AMSE, we have a STATCOM, which we have used, as I was telling you, in more than 100 projects. This is a STATCOM, which is a modular one. It's a 4 megawatt STATCOM, which we call it as DVAR STATCOM, and it's a 4 megawatt module which has 3 times overloads, which means for a very short period it can give 12 megawatts plus or minus leading and lagging. It also has we also have this control cabinet which can seamlessly switch other devices, so it can pull in the resources when it is required. So what we have done is we have I have just taken 2 examples of the grid code and how we are able to meet those grid codes. One of them is Texas. Texas is I think it's not as my colleague was mentioning, it's a separate country by itself kind of thing. So it's different from the Western as well as Eastern interconnection. So there is no connection between these interconnections. So they have a very evolved regulations. They talk about the power factor requirements, that is 33% of the net real power. Then they talk about set points between 0.95 and 1.05 pu. They also talk about the system sizing by themselves. Not many grid codes talk about that, but ERCOT does that, and they say that the overload can be included as a solution, and they also say that you can use mechanically switched capacitor banks and reactor banks to account for the losses. They talk about regulation mode, that is basically the voltage control with a 2% droop, whereas other grid codes they keep it open many times. They also talk about the LVRT, HVRT capability, which is out there on the right side. So how do we take care of this? This is an example of a wind farm in Texas. As you can see, this is I don't know whether you will be, yeah, you can see that it's a 200 megawatt wind farm with 2 buses. And when we did the study, we said that okay, this requires a STATCOM, and so we have provided STATCOM on 2 buses along with some reactors. There is you can see this. Okay, there is this. This is the controller, which is a DVAR controller, control cabinet, and this is the wind park controller. So you can have, I mean, you can make the DVAR controller or the STATCOM controller as the master controller, or you can also make the wind park controller as the master controller. So depending on the individual wind farm requirements and the requirements from the operator, we can do both the option. So here the DVAR controller, what it does is it pulls in the reactive power capability of the wind turbines, the reactive power capability of the inductors, and the DVAR reactive capability, and then it tries to meet all the requirements at the point of interconnection. So this is basically the simulations for the power factor requirements, wherein you can see that the dotted line is the requirement. This is on the inductive side. This is on the capacitive side. This is about 66 megawatts because it's a 200 megawatt wind farm. So by providing the required DVAR as well as the inductors, we are able to meet these. These are the points which are most difficult ones, but that's where I think the simulations help. This is the right-through requirements. Basically, you can see that you must have seen the HVRT requirement of the grid code in my earlier slide. So when such an event happens, so the DVAR goes down. This is red is DVAR, so it goes down and then it keeps the profile as per the grid code. And you can see that the grid code says that if it is within that, then the turbines are not allowed to trip. So you can see that the turbine output or the wind farm output has remained same, and it's not tripped. South Africa very recently, I think about 4 or 5 years back, they started with renewables. And they adopted the grid codes right from day one. So, and also they adopted the grid code in such a way that it is quite stringent. They also have a speed of response requirement added to the general grid code requirements. So these are the grid code requirements: regulation mode, that is the Q control mode, and power factor control mode. They have given an option of 4% or 8% droop, power factor capability of plus or minus 0.95. This is on the regulation side. On the dynamic side, they have this requirement of reactive current injection, especially when there is a deep swell or a sag. So they want you to inject current in this manner, going even up to zero. Level. And also this is the low LVRT and HVRT requirements. So I'm giving an example of one of the wind farms in South Africa, where again after studies we found that the STATCOM is required. So STATCOM was provided for this wind farm, and we used, instead of two single master controller, control cabinet, to control the requirements of requirements at the PCC. Once you provide and once you say that okay, this by doing the studies, by simulation, you can show that the wind farm complies to the grid codes. Then comes the real validation. So this is some of the field tests which we did to show that the wind farm behaves the way it is required or as per the grid code. So basically, this is the reactive power test from Q minimum to Q maximum. Then the voltage control test, you can see the deviation is within what is specified in the grid code. The power factor test and also the voltage control profile test. These can be done easily because these can be simulated in the field. Whereas transient requirements, it cannot be tested at site. There can be only simulations. So we did some simulations and then show that this is the reactive power current which needs to be injected into. So this point lies here. What happened also, there were some two events which really happened after a few months of commissioning of our wind farm, and then we again analyzed that, and then that came to some high-speed graphs. Through that, when we analyze that, again it's meeting the grid code requirements. So if we talk about India grid code has been evolving, and there is a draft grid code which has come out. The LVRT requirement was there in the, I think, 2015 grid code, but the new draft version, which is still being reviewed by the authorities. That is still to come, but then if we study that, they have some requirements of voltage control, talking about adjustable loop. Then there is a power factor requirement of plus or minus 0.95, like any other grid code. They have also added speed of control, speed of response, that is 0.95 within 1 second. It should come back to 95% within 1 second, which is quite fast enough. This is similar to that in the UK one. The LVRT and HVRT requirements are also mentioned in that. Again, I would like to mention that this is a draft grid code. It's still not come out. It's being reviewed. But in any case, these are the things which have been mentioned in the grid code at the moment. Another point which I want to mention is that it is not just the requirements at the turbine level, but also at the we need to look at the other reactive losses when we consider or when we do the simulation. So if we talk about 100 megawatt wind park and requirement of plus or minus 0.95 power factor, so turbines normally they are able to provide this plus or minus 33 megawatts of reactive power. Then there is there are losses at the transformers. There is a losses at the collector bus, and there is a loss at the big power transformer, which is connecting to the transmission line. So there are these inductive losses which need also to be accounted when we do the calculation. So totaling, even if you say plus or minus 0.95 instead of just 33 megawatts, we need to account for plus minus 50.5 megawatts at the point of interconnection. Of course, this could be provided with the help of capacitor banks. So going forward, I think the wind farm, many of the wind farms or few of the wind farms would be requiring a STATCOM and reactor bank or capacitor banks, and also control through these sophisticated controls. And similarly, what I showed earlier, meeting the reactive power capability, similar to the earlier graphs. So this is what is going to look like, in my opinion, if the grid code is approved the way it is already written and being reviewed. Thank you.
So were there any questions for Mr. Managoli?
Hello. Yeah. So this is Dhiman Chatterjee from IIT Kharagpur. My question is, see the STATCOM that you are showing here is being connected at a higher voltage like 132 kV or even higher. On the other hand, these wind turbine generators, they now with this type 4 wind turbine generators, you have a full capacity back-to-back converter, which is at a much lower voltage level, right? So, and out of those two converters, the grid side converter is capable of supplying reactive power. So, and that being at a lower voltage level, is it not economical that you increase the size? If you have some reactive power requirement that you feel that this is to be added, now you add capacity to that grid side converter at a lower voltage level instead of putting a large STATCOM at 132 kV, which is extremely costly, as I understand. So, what about that?
So the STATCOMs are not at 132 kV. They are the actually, if you see our STATCOM, it's a low. The output is 690 volts, and then we use a power transformer and connect it to the medium voltage. But what we do is we look at the point of connection and see that that the grid codes are satisfied at that particular point. So what you say, the STATCOM connection at high voltage is not there. This is the you can say the medium voltage or or a low voltage STATCOM. That's number one. Number two is that these can be provided in wind turbines, but then it's a cost economics. One has to see. The STATCOMs are provided at a wind farm level. So wind farm can be you can have 50, 60, or 100 wind turbines. So it depends on the cost economics also.
Yeah, but this is concentrated. This is at a single place. So if something goes wrong, the whole thing goes wrong. Whereas if you have a capacity addition in each wind turbine, then one may go wrong, but still overall there is a support still available. Giving one concentrated STATCOM still has this disadvantage.
I said that's the I think cost economics of the wind turbines. Wind turbines become very, very expensive, and then probably it becomes difficult again. And what you are doing is you are multiplying, say for example, there are 100 turbines or 50 turbines, you are multiplying that additional cost by 50 times, whereas here it's one or two. It's not much. I mean,
no, ultimately you are supplying the same bar. So ultimately you have to supply, given the same voltage level, you will have to add the same current capacity.
Okay,
so that way economics should not be difficult.
Maybe we can take that question further offline at
Thank
lunch. Thank you. Were there any other questions? And at this point, we could just open it up to all the speakers if you have any questions for them. Okay, so I guess we're headed to lunch. Thank you to our speakers for this for all their talks, and right, thanks everyone.